And today, with our intro to Grasshopper and Rhino, we're going to do a pretty simple, kind of raycast exercise where we're going to define a little parametric wall model, and we're going to extract the surface normals. And if you're not familiar with surface normals, a normal is just the vector perpendicular to the surface, right? So like if you do a lot of like finite element modeling, you deal a lot with local planes, right? And sort of the local plane of a surface, that z direction in the local plane is the same thing as the normal. And then, we'll use a dot product today to do a little flip test, basically, or to filter. And that I'll talk about dot product in a second here. We'll do a vector reflection, which is just kind of a simple formula for taking one vector and bouncing it off of another, or reflecting it over another vector. And then we'll do a projection from using our resulting vector to project onto the ground plane in this case. I mentioned dot product several times, and this is like one of my like first things I would say people should learn, because it's a really super handy in so many scenarios, and it's really quite simple. It just says that if you've got two vectors that have a length of 1, you might hear the term unitized vectors or normalized vectors, just meaning the length of the vector itself equals 1. Then you can take those two vectors, multiply their similar components. So the x of the first vector times the x of the second vector, the y of the first vector times the y of the second vector, and z, and so on. And then just sum those up, add those three together, and you get a value, or I mathematically call a scalar, but you get a value that is between -1 and 1, as long as they're unitized, the value between -1 and 1. And that is super useful because it tells you if the two vectors are facing a similar direction or not. So if you've got this vector and this vector, but you don't know if this one is pointing this direction or pointing that direction, and you can do a dot product really quickly with the two vectors, and you can figure that out. If they're pointing opposite directions, it'll be negative. If they're pointing the same direction, it'll be positive. And if they're pointing exactly the same direction, it'll be 1. Or if it's like halfway between, it'll be 0. So it doesn't tell you the plane of like an angle, but it more or less is kind of like indication of angle. So that's my nerdy favorite thing in the world. It's super helpful for lots of things. So let's move on to actually looking at Rhino and Grasshopper. So I'm not going to cover the installation of Rhino today, because I think that's something that should be able to figure out pretty straightforward. If you have any questions or you get stuck, let me know on that. You don't need to follow along with this. We're just going to kind of go from scratch. But I wanted to show everybody just this is Rhino is a super generic 3D modeling software. It doesn't have, like, Revit knows what a wall is, and Revit knows what a floor is. Everything is just boxes and lines and meshes and whatnot in Rhino. Super generic modeling software. So we've got about 18 minutes. So I'm going to kind of go fast today to blow through this. So the first thing I'm going to tell you is that Grasshopper is a built-in feature. Oh, popped up on my other screen. Is a built-in feature of Rhino these days. So when you download Rhino, you automatically get Grasshopper, which is great. And Grasshopper is just the visual scripting interface for Rhino. So let's think about what we need to make first our little parametric wall with our windows that we'll reflect off of, and start building that. So the first thing I'm going to do is I'm just going to use this control point curve, and we're going to define a let's define just a kind of squiggly line. And that's going to be our sort of plan view, what our wall looks like. And then we're going to start our very first Grasshopper script. So I'm just double clicking in the Grasshopper interface here on the background, and it pops up a little search. And the first thing I'm going to do is I'm just going to reference that curve. And you see this little hexagon means this is a container. So it's like a reference. So I'll grab that curve, or I'll create a curve container, and then I'll right click and I'll say set one curve. So I'll tell it, this container, that it references this geometry from Grasshopper, or from Rhino, sorry. So now I have, if I hover over this, it says referenced planar curve. So now I can output that curve to something else in Grasshopper. So the next thing we might want to do is let's turn this, instead of being a smooth sort of a spline curve, let's turn this into a segmented curve. So maybe, there's lots of ways to do it, but let's just do divide. Let's divide that curve and get points along it. So we'll take our curve and then we can have our number of segments. So I'll double click here and just a shortcut, I'll just type 12 and that gives me, it decided I probably am looking for a number slider between 0 and 100 if I type the number 12. So it gives me a nice convenient slider. So I'll put that in. You can see now that we're manipulating our model with our slider. Okay, and I'm going to speed up a little bit here just so we can get done. I'm going to next make a polyline and go polyline, and we're just going to take the points of that we got from that division and create a polyline. So now you see we've got straight segments between all those points. Great. So now we've got that. Now let's take that polyline and extrude it. So let's do extrude, which means basically just, pull it into 3 dimensions, right? And so we're going to take that curve and we're going to pull it in the Z direction. So I'm just going to do double click, type the letter Z, and now I'm saying the Z direction. So you can see that's done 1 unit. So these two squares are like a foot, 1 unit. And then we can say, let's go more than that. Let's just type, I don't know, 22, let's say. Maybe that's about right for us. Those two, you can't even tell the line between because they're almost linear. But there it goes, break it down. So now we've got parametric control of our model there. And then so that we have a couple more stories to our facade, let's just say, let's move. Could have done this a couple other ways, but let's do it this way. We'll say we're going to move that up, and we're not just going to move it up once. We want to make like 5 or 6 instances of it. So how about we do, let's do a series component. So series is going to let us make a list that counts based on an interval. So this has an input for the the starting number, how much to count by, or what the step size is, and how many total numbers you want. So we're just going to say let's do our count is going to be, I'm just going to type 11, and that gives me that 0 to 100 slider, and we want to move this up by 28 every time, so they stack on top of each other nicely. And again, we want this to be in the Z direction, so we provide the values to turn them into Z vectors. So now you see they're all turned into vectors there where it's saying move up by that amount. Plug that in, and whoa, there we go. Okay, so this, wait, why is that? Let's see. Oh, I'm sorry. I used the wrong slider. I didn't mean to plug this one. I meant to plug this one in. So this is the height, right, that we extruded to. That's the interval we want to stack at. So there we go. And you'll notice that the previous geometry from every step is still there, right, in Grasshopper. So it's basically every time you make a new component, it's just making a new object, right? You're always taking the old object, creating a new object. You're not changing it, you're making a new object every time. So if I don't want to see all those old objects, I can actually highlight all this, just drag and highlight, and I can preview off. So that means that I won't see it in the Rhino interface anymore. So that's kind of cool. And now we're tied to our geometry, so we can actually manipulate our geometry, and Grasshopper knows to follow all the instructions we define to create our geometry by running the script. Okay, cool. So now we've got a parametric curved kind of facade surface here. That's going to be our wall that we're going to reflect off of. And just the last step is let's get the center point. So we can do area. So using the area component is a good way to quickly get the center point. Oh, but first, instead of these being joined together surface extrusions, I'm going to blow these apart so that it's not like a piece of ribbon, it's actually a individual set of panels. So let's do deconstruct brep. Boundary representation is the word it uses for like a multi-surface type thing. Okay, cool. So now we've got a center point for all of these. So that'll give us somewhere to, sort of use to calculate our reflection. So now the next thing we got to do is we got to figure out where the sun is, right? Because we now have these points. We need to know what the angle of the sun is. So we need to sort of define a way to parametrically control the sun. So we're creating a vector that is going to represent the sun. So let's do this. Let's just do lots of ways to do this too, but let's do it this way. Construct point. There it is. We just do construct point. That gives us basically the 0, 0 point by default if we don't give it any inputs. And that's fine. Let's work with that. Okay. And then the next thing we're going to do is let's say that the sun is always by default, let's say the y direction is north. So if we say the y direction is north, and then we reverse that, so we can say south is the reverse of the north direction. So you can't see it right now, but it'd be like pointing this way, right? So let's say vector display, and just get a little preview so we can see this vector. And this wants the point that we're going to be placing the vector itself. Actually, let's just do that. And then a color, we don't really need a color, and a width. All right, so this is of length 1, this little arrow right now. So I'm just gonna, let's just multiply that vector by something to scale it up. Too big. All right, so that's our south direction, right? So now if you're familiar with solar angles, you kind of talk about solar angles in altitude and azimuth. Altitude being the incline to the sun, azimuth being the angle from, I believe it's from south. But so let's just rotate. Let's rotate this vector to kind of get a vector that we can control that tilts up and down. So let's think about how we're going to do that. So we take that vector and we'll do vector rotate. Where is it? Rotate a vector around an axis. Great. Okay, so we're going to take our vector, and I'm going to use the unscaled version of it. And then we're going to say the axis I want to rotate this is going to be this red line here, right? The x-axis, so that we can tilt it up. So I'm going to say this is going to be x. The unit x is what we're rotating along. And then we want an angle in radians. So let's say if in degrees, let's say we want 90. And then I'm just going to convert that to radians using the built-in kind of conversion rad here that just takes a degree, outputs it in radians, and then provide that to the script. And then now if I take that vector, oh, we might need to do negative 90. So that I don't have to do negative 90. Let's reverse our axis of rotation. There we go. So now we have a tiltable sun angle, right? So we took our south vector, we've now made it rotate along this x-axis. We've made a tiltable sun angle here. All right, and then the next thing we're going to do is we also want to be able to rotate that vector along the azimuth. So this is the altitude. We want the azimuth, so we want to be able to say the sun rises in the east, sets in the west, so to speak. So let's just really quickly do another little piece of vector math, and we're going to do another vector rotate. Let's say another vector rotate, and that vector rotate is going to this time be rotating about the z-axis, right? Because we want to take this And in plan, about the z-axis, we want to swing this vector. And let's just do this, and we'll say that's the axis. Our already rotated vector is the vector to rotate. And then let's do another rad conversion from degrees to radians. And then this time, let's do 45. Whoops, not 445. 45. And I'm going to change the value range of the slider. So I'm just right clicking here, and then I'll say negative 45. And then the max, I'm going to just do 45. I know that's not for everybody who's super into solar stuff. I know that that's not totally accurate, but we're going to go with that. Oh, that didn't change my max didn't get set. Hold on. Maybe I didn't press enter. Okay, so now the max is 45. So we're going to swing from 45 degrees one way to 45 degrees the other way. And now that's going to become our vector, our manipulated one. Okay, so now we've kind of got an altitude and azimuth calculation here, right? So we've got our altitude, and then this isn't exactly azimuth, but it's more or less the swing of the sun, right? Not perfect as far as solar goes, but it gets us a vector that is plausibly, the sun. We could consider to be the sun for this exercise. Let me make this a little bigger so we have a little more room. Okay, so now we've kind of got everything we need as an input side of things. Now we need to figure out if this angle hits this point, where does it reflect to? So we can do a little bit of math here, but the first thing we need to know is if we're going to reflect off of this, then we need to know what direction each one of these windows is facing so that we can do our reflection, right? And the direction those windows are facing is what I described before as the normal of the surface. So if we let's say we take all these faces. So here we've got a big list of all these faces when we exploded our sort of ribbons of faces into individual faces. So each item in this is going to be one of these rectangular faces or windows, I guess you could say they are. And let's get the plane of the surface, right? So I'm going to do this isPlanar command, and then I'm going to give that all of our surfaces. Oops. And look at that. All right, so you more or less from that get what, if you're used to making finite element models, what you might consider the local plane, right? This is the plane that defines sort of the coordinate system of all the surfaces. So now we need to reflect off this plane. What I'm going to do is I'm going to extract the z direction of each of these planes. So I'm just going to flatten this, which maybe get into that in future ones, but more or less I'm getting rid of the sort of nested structure here and going to a flat list of planes. And then let's take each of those planes and let's say deconstruct plane. And deconstructing plane is going to give us the different components of the plane, right? So, here, what is this? Boolean to plane. Oh, the plane is this output, not that output. Hold on. Okay, so this is the flag, if it's planar or not, and these should all be planar. And then we've got the surface plane. So now that's all of our planes. And now we got this vector that is the z of this plane. So not the global z, but the z of that actual plane. And so that is actually the same as the normal of the plane. That gives us the vector perpendicular. So if we do another, just to kind of demonstrate what we're looking at here, if we do another vector display and we say take the center point of all these and display, whoops, not that vector. We want to display our z, let's flatten this. We want to display our z vectors of all of these. If I zoom in, now we see these little arrows on all of these that are saying what direction the z vector is for all of these. We are running out of time. I apologize. I thought we'd have a little more time to go through this, but you're welcome to stick around. If you got to go, I totally get that too. But I'll just finish this out and keep recording. So if you need to watch the recording after, then feel free to do that as well. Okay, so a couple more steps and then we'll have what we need here. So basically we need to take all these little vectors and we need to reflect our sun angle off of those, right? I'm noticing that just the way we drew this line, they're all facing the wrong direction. I kind of want them facing out the other direction. So I'm just going to reverse those as well, reverse that vector. And if I plug that back into the preview for the vectors, now we see they're all facing outward on the side that we were kind of looking at as the outside of the building. Okay. So now that we've got that, let's do a little bit more vector math. We've got our angle of incidence and we've got our normals of all these planes so that we can get our angle of reflection. So I'm actually going to do this by creating a little custom node in Grasshopper. So I'm going to do this with the language C#, and we're just going to make a little component to do this. And that component is going to take in two vectors. So let's call this sun vec, and then let's call this norm vec. So we're going to create two inputs on our custom component, and I'm going to go ahead and say that these are of type vector 3D. And this one's also vector 3D. And so then we're going to say our sun vector is this vector, right? And I'm going to take the version of it before I scaled it for the visual, because this scaling is purely for us to see it. So I'm going to take the original version of it here, and I'm going to provide that as the sun vector. Actually, you know, I think we need to reverse that, because right now this is an arrow pointing towards the sun, but we want from the sun pointing towards us, right? So I'm going to just reverse that vector. That's going to be our sun vector. And then we're going to provide our list of normal vectors, which are all these little vectors that we calculated here, these guys. So I'm going to take those and I'm going to say those are our normal vectors. Okay, so then in here we need to define some logic for how to output, say, reflected vec, right? So we need to convert our two inputs to our output. So let's come up with some logic. So I'm going to double click into this component. And in here, we can define some logic in the language C#. There's also a Python version of this component for creating custom Python nodes if you want that. But this is the one that comes with Grasshopper and is not an installed package. So I like to use this. Plus C# is just a more robust language than Python, although I do love them both. All right, so here what we're going to want to do is we're going to have to do a couple things. First thing we're going to do is in order for our calculation to work, I just happen to know that these need to be unitized vectors. And they may already be unitized vectors, but I want to make sure, and it also helps me make sure that this component is generic for the future. So the first thing I'm going to do is I'm just going to say sunvec dot unitize, and all that's going to do is it's just going to convert the vector. If the vector is longer than 1, it's going to convert to make sure that it's a length of 1, and then I'm going to say norm vec. Is that what I called it? Norm vec, yeah. Dot unitize, and that is going to convert our normal vector to make sure it's of length 1. Again, those should already be length 1 based on what we did, but this is just going to make sure that that's the case, just for in case we need to use this component in the future when we might not have had a perfect length 1 vector. So the next thing I'm going to do then is we're going to do a little formula to basically come up with a output vector. So we're going to define a variable that's going to be a calculated vector. So I'm going to say the type of the variable is vector 3D. We're going to say vector 3D, and then the name of that is, I'm just going to call it reflected equals reflected new. Well, let me think about this for a second. So we just need to do the sun vector minus 2 times, oh, we need the dot product. Hold on, sorry, I'm just trying to remember this formula. So it's, we first need to get, we need sun vector times 2 times the dot, or minus 2 times the dot product times the normal vectors. Or bear with me on this for a second here. This is norm vector. I know that C# is probably new to people, hoping that kind of follow along with what I'm doing. But so we're going to say the dot product, which is going to be a double value, or same as a decimal basically. Double value dot is equal to, I'm going to call a built-in function. So this is vector 3D dot multiply. And we can just use multiply because we already know that our two vectors are unitized, and I'm going to multiply sunvec, oh, sunvec or sunvect, sunvec times normvec, right? Oops, not one. There we go. Okay, so this is getting our dot product, which remember is a number. It's going to give us a number between -1 and 1. And then that's part of the equation for reflecting one vector over another. And so we're going to say this is supposed to be sunvect. A reflected vector is equal to the sun vector minus 2 times the dot product times normal vector. That's just the formula, not something I'm necessarily coming up with for this. Okay, and then I'm just going to say our output reflected vect refvect is equal to what we calculated, which is REFL. Could have made that a little shorter by just saying this is equal to this, but it's okay to define that extra variable, I think. Okay, so that should give us the reflected vector. So let's take a look. No, what does it not like? Not exist. Oh, I put a T at the end of those. There's not supposed to be a T at the end of them. So this is sunvec. You guys can call me out if you see me making mistakes. All right, so we've got sunvec times normal vec, and then that gets us a reflected vector. Okay, so now we've got a list of vectors on the output. Let's take a look to make sure that looks okay. We're going to preview those. Let's just do the same thing as before, and then we're going to use this new list of reflected vectors, the output here. Okay, so our reflected vectors, let's maybe scale those up so we can see what we're looking at here. We're going to just take our vectors and we're just going to multiply them by, let's say, 100 so that we can see what they look like. And you put that into the preview, and there we go. So now we've got our, when the sun reflects off of that surface, where does it go, right? So that looks about right? The sun comes down, hits this spot, reflects off like that. Now I was going to go through and say, let's filter some of these so that if it goes, if it's pointed, if this wall continued to curve around, well, at some point we want to stop reflecting because it wouldn't make sense. But in this case, let's just skip that for the sake of time. And so now those are our reflection vectors. And the last thing we're going to do is we are going to project our points to the ground so we can see where those reflections would hit. So I'm just going to take our list of our area center points that we took before, and I'm going to say project. And which project do we want to use? Project an object onto a plane. And we're going to say the object we want to project is the geometry. Oh wait, I'm sorry. This is not going to project with the direction. We need a different project function. Project. We need project along, project an object onto a plane along a direction. So we want to project the points, and the direction we want to project them in is our calculated reflection vector. And the, oh, I'm sorry, I did that wrong. This is the direction. And then the plane we want to project into is just going to be the world XY plane. So I'm going to provide that there. And that should be then the points where the sun reflects off the middle of that window where it would hit on the ground. So that's the whole thing. Now we have our two controls where we adjusted the angle of the sun, and we can now follow throughout the day to find our locations where the sun reflects off and hits from every individual window. Okay, thanks for those of you guys who stuck around. I know that was a really fast run through of that. Probably could have done the whole meeting on just that one presentation, but I appreciate you guys sticking around. I'm still available if anybody has any questions or wants to chat a little bit about this before you go. But otherwise, thank you guys for coming.